There. I just paired up on stuff. I'm 31. Yeah, I guess so. Yeah. I showed him that. And I was like, I know how to find. All right. So the plan is, I think, to get through just a little bit more. Just get to a point where it's sort of, we touch base with something we saw earlier, give you guys an idea of what this chapter is kind of all about. And we're probably going to stop there. I think I might get through that today. And we'll use the last couple of classes to just kind of go over problems related to or adjacent to the final. Should be posted this afternoon. That's my plan. I might not get through everything today. If I don't, I'll do a little bit on Wednesday. I'll be available next week. Questions or what I think. Okay, so where did we leave off? Well, we were talking about of integers. We were talking, and we sort of, I gave some pictures of what things looked like in the ring. This ring, see, and so we didn't get too far in there, but I want to state a couple of propositions. This first proposition is not hard to prove at all. But okay. So yeah. I'm going to sort of, what I'm going to do here is prove the pictures I showed you last time are indeed correct, or at least there's an ideal that looks like that. So let's let, it's a general proposition that R be three integers of an imaginary number field So we have that every non-zero ideal zero ideal bar the sublattice and possibilities is congruent to 3 or then a sublattice A is an ideal and only if A. And then on the other hand, here, same statement, but we have to do a couple of placements. Other cases, T is congruent to 1, 1, 4, and sublattice A is eta. Okay, so we throw this to you guys. Kayla, I don't know if you guys watched problem review Friday. Kayla asked a question about what's the deal with all this congruence mod 4. And I kind of want to make sure everyone understands. So what the project is here in this chapter is we're looking at the specific class of rings, the rings of algebraic integers of the quadratic number field, imaginary. The reason we're doing that is it gives us a way of sort of expanding our understanding of sort of basic rings, see where some of the things that we would expect kind of go wrong. When we do this, when we look at this class of rings, they do sort of divide into 2 different sets. Right? One set has a certain look. You can actually draw the lattice of elements of these rings on a plane. One set, it looks like a rectangular lattice. So it's like a rectangular lattice. The other set is this isosceles triangle. It's like a rectangular lattice, but you put the center point to the rectangles. And those are divided up into these 2 cases into 3, one is 100, 4. Furthermore, when you look at these 2 cases, the kinds of ideals you get also. All right, so that's why you see this. And if you'll recall, this delta, the notation Artin is using for this delta and eta, is that delta is this square root of d. Eta, in the case when d is equal to 1, or d is congruent to 1, not 4, there's also this center point of this rectangle. The notation. All right, so let me throw this to you, this type of proposition, and ask, how do you prove something like this? Verify this. Take part 1 and say, let me get us started. So for part 1, to recall what R is. When D is congruent to 2 or 3, R is equal that all of these form normal sums, A plus B times delta A B, right? That's what I was saying before. This is that rectangular lattice. B is, remember, delta, remember, is purely a measure. It's the square root of B. B is a negative number, so it's some scale of I. So, okay, so with that in mind, how would we go about definitely use state? Then we had a sublattice A. Let's see if it's
Assume A is an ideal, show that delta A is contained in A. To show that delta A is contained in A, assuming A is an ideal.
okay, so let's assume, so if we'll go one way first. So A is a sub, it is ideal. Then so Garza, what are you saying then at this point?
I was just assuming,
What does it mean to be an ideal of a ring? What's the definition?
Multiply any element of the ideal by any element of the ring.
Right.
An element of the ideal.
Right, it's closed under, well, that's one part of it, right? One part of it is exactly that. That's sort of the crucial part. The other part that we kind of forget, maybe to mention sometimes, is a subgroup under addition. So it's an abelian subgroup under addition. Just think of the additive operation. Then it satisfies this additional property that John just mentioned, right? That you multiply any, if I take any element from the ring, I multiply something in the ideal way, get back to something. So with that in mind, what can we say? You guys just read about rings all weekend? I thought you guys would be talking about stuff. I had that experience when I was
if delta is contained in our ring, then just delta times A by definition.
Delta is never. If A is 0, B is 1. Delta is the delta, right? Is an element. So delta's in here. So to be an ideal, it means if I take anything in this set A and I multiply by delta, it has to still be an A. That's one of the defined properties. By definition. From delta, this is the set of all of the elements. Delta times, we multiply a set by just one. All right, so that's one direction. Now let's suppose it is an ideal. All right, let's suppose it satisfies this property and go the other way. Firstly, we want to do the case for 2. This is the same kind of. Suppose we want to show it's an ideal. Well, it's a lattice, so it's a group under addition. That's part of the definition of our lattice. I don't have to worry about the group property. We just need to show that for any element in R, I multiply A by that element.
if we know that A and delta, like if A equals 1 is in there and delta is in there, we can construct it.
So A equals 1, which is, so,
Like a little baby.
okay, so baby A, or otherwise known as lowercase. Baby is better. Good, yeah, so let's do this, let's take what you're saying. So we know, okay, so let's just do the whole thing, so let's suppose that alpha is an element, capital A. And we'll take any A plus B delta. Okay, well then, what do we say about A times alpha? Maybe A times capital and baby B. What do we say about these?
Not under the assumption that A is not good, right?
We are not, because we want to assume our conclusion, but we are under the assumption that A is a lattice. We know that our lowercase a and b are integers.
So A alpha and B alpha is so
Yes. Because it's a lattice. A lattice means it's a group. But when you multiply by an integer, let's say a positive integer, you're just taking a sum of that element with itself a certain number of times. And since it's closed under the sum operation, you get that it's that these guys are in A. If it's negative, then you're having an added index. But now we also have delta times B of alpha, because B alpha is in A, is also in A by the fact that we've got this assumption. So then putting this together with a distributed property, we get that A plus B delta alpha A alpha plus cancel lattice. Okay, so part 2 is the same exact argument, but just now knowing what that are, the only difference is that we replace this with A. Okay, guys, good warm up. Okay, so then, yeah.
How did we know that A was a lattice in our second part of this?
Well, that was an assumption. What we're trying to prove is this statement: a sublattice is an ideal if and only if this is true. So really, the assumption is that we have a sublattice A. We're saying it's an ideal if and only if this. So this is sort of the statement.
Okay, so we didn't need to prove it.
We did not. The questions? All right. So let's talk about this next line. So let R equal this number field. That's square. I don't know why. That's how he's writing this. But this is sorry. So then he just mentions this lattice that I showed you last time, a picture of integer combinations of 2. Two and 1 plus delta is an ideal. I gave you guys an expression for this, a different way of. So there's a couple of things to say. So this is, let's call it 8. And it's one way of writing this is ideal generated by this, but this is what we want to prove. So maybe I should write that. I'll just write it the way here. So I'll say 2a plus 1. Certainly a lattice. These two things are linearly independent as elements of linearly independent over the reals. A formula. So the expression I gave this, you can see, is I gave a different expression for this. Just this. I think, I don't know, is that clear to everybody? That's true. Good, anybody? Nobody sees. Okay. All right, so let's see. Okay, so maybe I may use a different name. Let's see. Okay, so let's say you had something of this form. Well, then I have 2a plus b times 1. That would be this guy. Right? And then this guy would be b. So, well, clearly those two are congruent on 2. I got 2a. So 0. As I'm saying, this expression, if I were to rewrite it, would be 2a plus b delta. But this is my a tilde, this would be my b tilde. But they're congruent on 2 because 2a just goes to 0. Something that's 2 is 0. On the other hand, if I had, so this is contained in this. On the other hand, if I have an a tilde and a b tilde, and their parity is both even or both odd, I can say, all right, well, like let's say they're both even. Well, then I can take this, since b here is equal to b tilde, I can just take b equal to b tilde. Then I can add any other even number to get the other even. So they're both even, I can certainly see that part of this is in there. Now, if they're both odd, the same kind of argument applies, is that I just take b equal to b tilde, and then, okay, I've got an odd number. All odd numbers differ by some multiple of 2. So I can just put a in for whatever that multiple is. Okay, so this is also. This same, I'm just saying, okay, it's just a little exercise, but you can go through it, and it's just a way of representing. And why do I mention it? Well, because, I don't know. I mentioned it because I like that description better, but also because I guess my perspective here is that I can take delta times a tilde plus b tilde. I can check. I A tilde delta plus or minus 5. Now I know, okay, so now I know negative, I've got B tilde, I'm moving to minus 5, B tilde. Like, mod 2. And negative 5 is conquered to 1 mod 2. Right? Odd numbers are all conquered. 1 times anything is itself. I mean, maybe I should have done the other. Sorry. I mean, B tilde is conquered to A tilde mod 2, then negative 5 B tilde. 6 B tilde. But that shows that and we use proposition. Now, this kind of seems a little strange. Like, okay, we have all these big general theorems, and then you look at this one particular case, and then we write down one particular ideal. Seems a little like going the opposite direction of where we were going, which is fine. But and again, I showed you this picture last time here of this ideal. So this is a picture of the whole ring R. So this is our R, which is in this case is the and then this ideal here, the red one is just the set of points inside of the sublattice. You can see it's not a square or a rectangular lattice. Right? It's got this sort of range. So why would we go to this kind of one particular example? And the reason is that this is sort of this example is sort of the example. That's the non-rectangular example in this ring of ideals. See that this kind of well, I don't know. I don't want to say we'll get to it. So this is a particular good example that gives us a lot of other things. Okay. All right, so now we use this to kind of classify all the ideals inside of this particular ring. This is this theorem. Theorem. 13.3. While we won't do it in this class, there's a classification for many of these. This is a good prototype. But our and a non-zero ideal. Alpha. A is a lattice. I mean, it's a subgroup of this. This is already a lattice. We have a sublattice. So what we can do is we can take alpha and A. An element, non-zero element, a minimal distance to the origin. The minimal norm, that means the distance to the origin. Euclidean sense, right? In just the sense of distance of the plane. So then either one of the two things happens. Alpha and delta alpha are basis. Then A actually ideal. By alpha. Or two alpha and is 1/2 alpha delta alpha basis. Alpha A is not principal. This is again, I mean, what we're looking at here, these cast of characters are the cast of characters that don't fit into this nice scheme of Euclidean domain, principal ideal domain, unique factorization. So we should expect to see some non-principal ideas. Now, Artin is very poetic in this chapter. So if you get a chance and you like to read nerds talk about the things they love, you should read through this chapter because he does talk about it in a very kind of flowing way. How his love for the subject comes through. And what he says in this, after this theorem, is really, I think, worth understanding, which is that, you know, if you're looking at all the ideals of this particular, they do fall into two camps. One camp, they look like the ring itself. Right? In other words, if you look at them as a lattice, instead of drawing them like as red dots, you draw blue or something, whatever, put some color on it. Then that lattice will be up to some kind of dilation and rotation, exactly like the original ring of integers. It will look like just a rectangular lattice, the same sort of ratio of sides. It's similar. On the other hand, it could be in case 2. And if you're in case 2, up to again some dilation rotation, will look like that ideal we just saw on the red one. So these are the two possible ideals, types of ideals that you get. And that's that fact does happen for all of these imaginary. And you get, it's not two types necessarily, but you get a set of types of sublat. Finite set. Everything is some sort of scale, and everything's similar to one of those types. What's more interesting, which he goes into later, I don't think he goes into it at this point, is that those types form a group. Those prototypes form a group called the class group. That class group tells us a lot about factorization. Really. So you go back to group theory and you start getting some interesting things from group theory, finite groups, that tell you a little bit about your brain. Really cool stuff. Cool. And it's not, doesn't end there. I'll go one step further. There's an analogy of all of this. We're talking about numbers and factorizations. You hate numbers, we hate factorizations. There's an analogy here, though, to geometry. If you take this ring, these quadratic algebraic integers or the quadratic number fields, these rings are all sort of like one-dimensional rings. In a very rigorous sense, there's a notion. But there's, of course, one-dimensional spaces in algebraic geometry where you consider curves, and we talked about them. I said, have these cool equal spaces inside. Look at curves with some punctures. You got like donuts, glazed donuts, hungry. Things like that, right? These can be described by a single equation, complex numbers. Of course, so you have some single equation inside of this given by a single polynomial. And of course, you can take the quotient, right? Take this ideal quotient. This ring is also one-dimensional. You can study its ideals. And its ideals are very interesting. They correspond to sort of sets of points on these curves. And there's a group that's analogous to that ideal class group that I was just talking about. That tells us a lot about the geometry. So algebra really does unify, like some basic ideas in algebra can unify sort of number theory, geometry, a lot of different different concepts and different questions. It's really a great subject, but of course we won't get into all of this, but I want to kind of share it. All right. Let's prove this theorem. And it's not hard. It's some kind of lemma. And we're just going to make a comment about the next section. Maybe tomorrow if we don't have time. So how do we prove it? So the proof is very nice. It's very specific to this example. It's not some general thing. But very nice proof. It revolves on some lemma that he has this sort of geometric. Not a hard lemma, but that's stated. So he says, okay, so let's let A be a lattice. And R, it's a real number, be the minimal this is something strange. Okay, so that's the minimal distance between any two elements. And they said, all right, so let's let n be a positive integer. And then here's the statement. So the statement is the interior of a disk radius 1 over n r about a point 1 over n times gamma contains no it didn't say something. I'm sorry, I didn't need to say that. I need gamma to be in. Sorry, I didn't write this down. Gamma be an element of A. 1 over gamma, 1 over n times gamma contains no element A other than in other words, it may not contain this. Just doesn't contain anything else. May or may not. You understand that? So he's saying, okay, here's a lattice. Take some element. You've got this number r that's just like the minimal distance between any points. some gamma in it. And I'll look at 1 over n times gamma. It may or may not be in the lattice, 1 over n. But then if you take a little disk of that small radius, 1 over n times r, nothing else is going to be in there except potentially that. The proof of this is really just kind of very easy. It says, okay, well, suppose otherwise, data. Yes. Well, what does it mean to be in the disk? It means that if I take the difference, the data and one in the center, this has, I'm putting absolute value around it, but you think of this as the norm. Distant, means the norm is square root of this times non. This is less than 1 over n times r. That's what it means to be this. Multiply everything by n. Take absolute value or norm. The n will come in, so I'll get n beta minus gamma. But this is in. So I'm assuming beta is an element of my lattice. So n times beta is less. Gamma. So r is the minimal distance between any two elements. I've got something of smaller distance, so they must be equal. Beta. So that means that beta is the same. All right, so okay, so now he uses this lemma to prove the theorem. So let's take a look. So how do you prove the theorem? Okay, you're starting with this alpha, and you ask, okay, well, what could A be? What could A be? I've got an element that's the smallest norm. I know A is an ideal. So I can certainly multiply this element by anything in my ring and get another element of A. In particular, I can multiply it by delta, by square root of -5. That will kind of rotate it by 90 degrees and then dilate it by, square root of 5. So I'll get two elements that span a basis if I do that. I'll get alpha and I'll get its multiplied delta. I can take the span of that, and that will give me a lattice inside of it, inside of mine. And then the question is that all of it, or is it not? So the first case is it's all of it, right? The first case is saying, okay, if I do that, I get everything. So to see that the only other thing that can happen is this, we'll say, okay, let's assume we don't get. So we don't get everything. What else could we do? That's where we'll start with the proof. You're going to want to use the lemma. The proof of theorem. So suppose alpha and delta times alpha not equal to beta. But there's a beta. Not. span this. Integer span alpha. Now, we had this, we talked about lattices for a little while, back when we were talking about isometries. And one of the lemmas back then was that you could, if you had a sublattice and you took any element in R2 or C, if you want to think of it this way, you could translate that element inside of some parallelogram given by the basis. So what I'm saying is, let's say we have alpha here. Here's delta times alpha. If I have some other element way out here, well, I can take this rectangle and I can just I can move it around, right? I can translate it and I'll get a big rectangular lattice. And so this red point will live in one rectangle. I can translate that using the elements that are span of alpha plus delta alpha back into this rectangle. Just translate it. So in other words, there's some translate of this that lives inside of here, that parallelogram. And that will also, if this red point is not in the lattice, then this red point over here will not be in that side. The translate won't be in the lattice. That's generated by alpha. So we're going to assume that's the case. Beta. This. Right. And now, Artin has this picture. I mean, it's a nice picture. I gotta say, I like it. So I'm gonna take it. I don't want to reproduce it. Yeah. Oh, it could be on the boundary. It could be on the boundary. It could be in the interior or the boundary. So the lemma I'm referring to is just to say any other element in R2, I can translate it to get it inside of that rectangle. And so now I'm assuming I've got a beta that's not in the lattice somewhere. Let's just translate it so it's in this particular rectangle and not in the lattice, meaning not one of the vertices. So what he does then is he says, okay, well, let's take a look at what can happen. He says, let's creatively cover this rectangle. And he does so with, he says, okay, well, alpha by definition in the theorem is minimal norm, meaning it's the minimal distance to the origin. And so this R that we had in the lemma is precisely this distance here, alpha 0. So he takes this disk around alpha, but then he takes the same disk around these 4 points, 4 corners of the rectangle. And he takes a half of this here, and a half of this guy. That gives you that one. And then, okay, this is a half of some point out here. Some lattice as well. So taking half points of the lattice, and he's taking half radius disks around it. And says, look, they cover this rectangle. Beta's in one of them. Beta must be in at least one of these. Write that down. Beta lives in one of these disks. But these, this lemma tells us that the only element of the lattice that can live in these disks are the center points. It's the only possibility. So if beta is in one of these big ones, big disks, then it has to be precisely one of these vertices. But we assume that beta was not one of those vertices. It's not in the lab. So it's not one of the large disks. So it must be one of the small disks. It's either here, here, or here. Well, this point here, this is 1/2 alpha delta. And this point, well, certainly if it's this point, we can subtract alpha and we can get to this point. If we subtract alpha from this point, we'll get to this point. So we don't need to really consider that. Or it could be this point. That point is alpha, is 1/2 alpha plus delta alpha. So if it's that point, guess what? We're in the other case right here. The only thing we need, and then we're done. So the only thing we need to do is just rule out this case. And for that, we need to consider what happens when we multiply by delta. Here. Let me just finish this argument. Take 10 seconds. We get that. L squared is -5. And this, by definition of ideal, has to be negative. But then if I add 6 alpha, which I can, 3 alpha, sorry. If I add 3 alpha, this, I'll get alpha over 2 is net. Right? But that's over here. And alpha was the smallest element that was the closest to is a contradiction. All right, guys, I'll spend like 5 or 10 minutes, maybe 15 minutes next time, just wrapping up. And then look over the problems I send out, and I'll field questions and we'll talk about techniques we use to solve these sections.
Are we gonna have a regular one?
Yeah, don't do the homework. Don't worry about it. I picked one topic from each of the major subjects to ask a question on the final one. I think it's going to be about 5 questions. And so, yeah, don't worry about the homework. I'll roll that into the last. No, I'm going to ask the group theory question, but just like one question. It's sort of. Everything.